So we're going to talk about double integrals in polar coordinates. So just a quick reminder in polar coordinates, our conversions. X equals r cosine theta. Y equals r sine theta. R squared equals x squared plus y squared. And tangent theta is y over x. For our conversions. So what we want to do is we want to develop this idea of a double integral rather than our region in the xy plane being rectangular sectors. We want them to be polar sectors. So let's draw a picture of what we're talking about here in the polar plane. So this is pi over 2 and 0. So we have a curve here, a couple of curves in this plane, and we're going to divide them into sectors. So I'm interested in this region here, and we're going from theta equals alpha up here to theta equals beta. And what we're going to do is divide this sector into polar sectors. So I'm going to take a bunch of little radii and divide it up like so. And then I'm going to divide it this way as well. So we're dividing it into these little polar rectangles. And this is our region in the xy plane. And we're going to take a look at one of these polar sectors and come up with an expression for the area of that polar sector, and then we can use that in our double integral. So this little piece, if we're going from here to here, we would call that little distance delta r sub I. And the difference in theta values in one of these sectors would be delta theta sub I for the ith little sector. And the coordinates right in the middle of this sector, we're going to say the coordinates there are r sub I theta sub I. So let's so we're dividing our region into these little polar rectangles. We want to come up with an expression for the area, and then we're going to we're going to use that area just like we did in rectangular coordinates to come up with an expression for a double integral using polar coordinates. So let's magnify this one little sector. I'm going to draw that over here. So here's just one of those sectors here at r sub I, theta sub I. So this is our region, and just like we said before, this is delta theta sub I, our change in the angle. And we're going to say this is r equals A and r equals B, and the length here is delta r. And so our region is what we call our polar rectangle. And do we remember what is the area? The area of a circular sector with how do we find the area of a circular sector? Do we remember that expression? Okay. So the area of a what's that? Kind of like a triangle. So we're talking about the area of a sector. We mean like this wedge shape here. So the area of a circular sector and by circular sector I'm talking about the whole entire wedge shape there, is with radius r and central angle theta is 1/2 r squared theta. So that would be the area of this whole wedge shape. So the area of our region is going to be the big area, the big sector minus the small sector. Is, I'm going to say A equals 1/2 b squared delta theta minus 1/2 a squared delta theta. And I'm going to factor my common terms, so we'll say that the area is 1/2 b squared minus a squared delta theta. And then we want something a little nicer that we can work with here. So to do that, we're going to factor b squared minus a squared. And I'm going to write that as 1/2 a plus b, a minus b, delta theta. And then we look at this expression and we say, what is, yes? Did I do it backwards? A squared, yes. I had my negative sign in the wrong place. There we go. What is this expression 1/2 b plus a? What do we get when we add two things together and divide by 2? What if your score on one test was 92 and the other was 87, and you add them together and divide by 2? What do you get? Average. This is the average radius in the sector. So we write that as 1/2. We write that as r bar. And b minus a is delta r. So r bar is the average radius. So there's an expression for the area of this little region, this little polar rectangle. The average radius times delta r delta theta. And what we're going to use this little piece of area, that's the area of this little sector, we're going to use that to come up with the volume bounded by a curve. And the region in the xy plane, or in the polar plane, is this little polar rectangle. Is everybody clear with what we've done so far? All right. So we want the volume to come up with this expression for a double integral. We want the volume bounded by r under f of xy. So we're doing the same thing. We're building little prisms, and this little piece that we just talked about, this average, this r bar, delta r, delta theta, is the base of our prism. We're saying this is approximately a rectangle. So the volume is, that we have under this curve is approximately the volume of a rectangular prism. So this is going to be the base, and f of xy is going to be our height. So this volume is the volume of one prism. And then the volume of one prism, and then we're going to sum all of those prisms over the unit. So we're going to sum that over the region. So the volume of one prism is f of xy, and I'm going to say x sub I, y sub I. We're talking about one prism in the region, delta a sub I. And our delta a sub I was that r bar, delta theta. And the r bar at our particular location, delta r sub I, delta theta sub I. And we want to express this in polar coordinates. So f of x sub I, f of y sub I. We need to do our substitution for x sub I and y sub I. So we're going to say this is f of x sub I cosine theta sub I, sorry, r sub I cosine theta sub I, comma r sub I sine theta sub I. I'm making my substitution for x and y, x sub I and y sub I. And then we have our little area element, r bar sub I, delta r sub I, delta theta sub I. So that's the volume of one of those little prisms. We're going to sum that over our region, sum the volumes of those little prisms over the region. And finally, we get that the volume equals a sum, I equals 1 to k, however many subregions we're dividing this into, of this whole volume element, f of r sub I cosine theta sub I, r sub I sine theta sub I, r bar sub I, delta r sub I, delta theta sub I. And then if we take the limit as the size of our polar rectangles gets smaller and smaller, so this delta a sub I that we come up with here, this delta r bar, delta r, delta theta, as that becomes smaller and smaller and smaller, this corresponds to our definition of a double integral. The sum was our definition of a double integral. As we take the limit, as that delta a sub I gets smaller and smaller and smaller. So we're going to define our double integral in polar coordinates as the double integral of this quantity. So the double integral over R of f of x, y dA is that sum. So we're going to say this is the double integral over r of f of r cosine theta, r sine theta, r dr d theta. As our little delta a sub I gets smaller and smaller, the average radius is just the radius of that little subregion, and then delta r and delta theta become dr and d theta. So this is our double integral in polar coordinates. This dA in polar coordinates will always take this form. It's always r dr d theta when we're using polar coordinates. So this equates to dA in polar coordinates. So this, when you're using polar coordinates, this quantity r dr d theta will always appear in your double integral. And there was a Simpsons episode way back when Lisa went to a gifted school and in elementary school, and they were all doing calculus, and they did an integral, and everybody started laughing, and she didn't get the joke. And it turns out that the integrand, the teacher explained, the integrand had the quantity r dr r, and everybody laughed at it except Lisa because she didn't get the joke. Whenever I see r dr d theta, I think r dr r. But don't put r dr r in there just because of that. So this is our double integral in polar coordinates. And I'm going to change this. Instead of r, let's make this an s. Just to remind ourselves that the region in the xy plane, we have to convert to a region in polar coordinates. So we need to turn our integrand, we need to convert our integrand into polar coordinates. We also need to express our region in the xy plane in polar coordinates as well. And so just like we did when we talked about these in rectangular coordinates, this doesn't tell us how we evaluate these integrals. Well, we can use something similar to Fubini's theorem to evaluate these double integrals, and we evaluate double integrals in polar coordinates as iterated integrals in polar coordinates, just like we did with rectangular coordinates. So to evaluate these, so the integral of s, and for this first one I'm going to say alpha less than or equal to theta less than or equal to beta, and g1 of theta less than or equal to r less than or equal to g2 of theta. So the double integral, this double integral, I'm going to say r f of xy dA. We evaluate this as an integrated integral, integral from alpha to beta, the integral from g1 of theta to g2 of theta, of f of r cosine theta, r sine theta, r dr d theta. And what we're talking about here is called a radially simple region. And if we drew a picture of the region, we have something like this. So this would be this first one. So theta is going from alpha to beta. And this is going to be G1 and G2. So this is a radially simple region. And most of our regions in polar coordinates are going to be radially simple. We usually express r as a function of theta. It's not that we don't do it, but we usually don't express theta as a function of r. Usually r is expressed as a function of theta. And then for if we do have a different kind of region, so if we have a less than or equal to b, less than or equal to r, less than or equal to b, and h1 of r less than or equal to theta, less than or equal to h2 of r, then our double integral becomes it's still an iterated integral. The integral of r over r of f of x y dA equals the integral from a to b, the integral from h1 of r, h2 of r, same function, and this one's going to be r d theta dr. And this one we call angularly simple. And our picture there, we have something like this. And then our function looks like this. So this is r equals a, r equals b, and this is h1, and this is h2. And the difference here, for a radially simple region, we're drawing our rectangles radially, our little representative rectangles, and here we're drawing our representative rectangles angularly. And it's most common to see our double integrals in polar coordinates in this form, and our region will look like this. All right, so what I want to do next is just go through an evaluation in polar coordinates, and then setting up a few double integrals in polar coordinates. For regions with circular symmetry, polar coordinates are going to make integration way easier than rectangular coordinates. So questions before we go on? Okay. Let's look at this double integral. So the integral from 0 to a the integral from 0 to square root of a squared minus x squared x dy dx. So I look at this thing and I say I don't like the square root of a squared minus x squared that we're going to end up with in our integral. Let's see if we can simplify this. Let's change this to polar coordinates. So first off, this tells me that the limits of integration say that 0 is less than or equal to y less than or equal to square root of a squared minus x squared. And it says 0 is less than or equal to x less than or equal to a. what is this region? Let's sketch our region in the xy plane. What is this region? Y is less than or equal to square root of a squared minus x squared. It's a circle, and we're only getting the part above the x-axis because we have a positive square root. And what's our radius of our circle? A. So there's A. So in polar coordinates, let's change this to polar coordinates. So we're getting x equals 0 to a, y equals 0 to square root of a squared minus x squared. So in polar coordinates, r varies from 0 less than or equal to r, less than or equal to, what does our radius vary between 0 and a? Theta, less than or equal to for this region. Sorry, 0 less than or equal to theta, less than or equal to pi over 2. So in polar coordinates, we have the integral, and here's where it might help you to write in your variables. Theta equals 0 to theta equals pi halves. The integral r equals 0 to r equals a. And x is our cosine theta. And then dA is our dr d theta. And we combine these two r's, so I get the integral from 0 to pi over 2, integral from 0 to a of r squared cosine theta dr d theta. And this one is easy to evaluate. We take the integral of dr, r squared dr, we get r cubed over 3, evaluate it from 0 to a. And then our theta integral is just the integral of cosine theta, which is easy to do. So this one is an easy integral to evaluate. And our limits of integration are both constant. Yeah.
That theta is 0 and both bottom
0.
Oh.
Questions on how we set that one up? Okay, let's look at another one. Let's find the volume inside the hemisphere z equals the square root of 16 minus x squared minus y squared. And outside the cylinder, x squared plus y squared equals 1. So on for these kinds of problems, it's always, I find it very helpful to draw a little picture. So here's my coordinate system. Here's my hemisphere, top half of this sphere. And here's my cylinder, like so. And this cylinder is going to cut through the sphere here. So we want the volume inside the hemisphere and outside the cylinder. So we're talking about this piece that's out here. So there's a picture, kind of a picture of what we're looking at. We need our picture, we need a region in the xy plane. So on the xy plane, and when I set these up, I usually draw both of these pictures to get an idea of what we're talking about. there's our region in the xy plane. The cylinder intersects the xy plane in a circle with radius 1. And when z equals 0, x equals, or sorry, when z equals 0 and y equals 0, I get x equals 4. This ends up being a circle radius 4 in the xy plane. So what we're looking for is the volume under z bounded by this region. So this is our region, this is our surface. This just gives us, this tells us part of the boundary of our region. So in polar coordinates, how would I write my function z? Z equals the square root of 16. I'm going to write this in polar coordinates. Minus x squared minus y squared. X squared plus y squared is what in polar coordinates? R. So this is going to be 16 minus r squared. Z equals 16 minus r squared. So my volume is going to be the integral. And I'm going to multiply, I'm just going to do this region and multiply by 4. So volume is going to be 4 times this, and I should say this is 1/4 of r, because the region goes all the way around. So the volume is going to be 0. The 4 times the integral from 0 to theta is varying from 0 to pi over 2. R is varying from 1 to 4 of square root of 16 minus r squared, r dr d theta. And we have this r here, and we have a 16 minus r squared. So we have an r for our u substitution to do this integral with respect to r. So that makes it nice. So let's evaluate this one. I get the volume is 4 times the integral from 0 to pi over 2. When I evaluate this integral with respect to r, I get minus 1/3 16 minus r squared to the 3/2. And that's evaluated on 1 to 4. And this is going to be the theta still. And then when I evaluate that, I get the integral for the integral 0 to pi over 2 of 1/3 of 15 to the 3/2 d theta. And finally, I evaluate this out. This integral is easy. Integral of 1/3 15 to 3/2 d theta. And I end up with 10 pi square root 15. So this one turns out to be an easy one to evaluate. In rectangular coordinates, this would be a fairly difficult integral to evaluate. Questions there? All right, let me pick out another one here. All right, let's find the area using a double integral. finding the area of r equals 3 cosine 2 theta. And this one, you'd either be given a graph or you'd be using your calculator to find the graph. This is a Rose curve. We'll do that. So this looks something like this. And it intersects here at 3. So we want the area. So the area with a double integral, the area is just going to be the integral, double integral over our region of dA. So that's what we did in 14.1. And since we have this Rose curve, we're going to do our area in polar coordinates. So what do we need to do to find our limits on theta here? How do we find our limits on theta? Remember with curves in polar coordinates, sometimes they can be traced more than once on the interval 0 to 2 pi. So we need to figure out what limits on theta trace out a petal. So what I want to do is find what we'll do is find the area of half a petal and multiply that by 8. If we look at this graph, half of a petal is traced out between 0 and pi over 4. Because when theta equals 0, my radius is 3, and when theta equals pi over 4, my radius is 0. So that's going to take me from here to here. So my area is going to be 8 times the integral from 0 to pi over 4. And my radius is varying from what to what here? Zero to 3 cosine 2 theta. And my area element is r dr d theta. So we're trying to find the area inside this region, so my radius is going to go from 0 to out to my function. So I evaluate this integral, I get 8 integral from 0 to pi over 4 of r squared over 2, evaluated on 0 to 3 cosine 2 theta d theta. Does this 1/2 r squared d theta, does this look familiar? From first semester when we were finding area using polar coordinates with a single integral. The area of a polar curve was 1/2 r squared d theta. So after we evaluate our first integral, we end up with our integral in polar coordinates in the plane. So this is going to be 4 integral, I forgot my pi over 4 here, pi over 4, 0 to pi over 4. R squared is going to be 9 cosine squared 2 theta d theta. And now how am I going to evaluate this integral of cosine squared 2 theta d theta? You remember our identity that I said would come up a lot? Cosine squared 2 theta is 1 plus cosine 4 theta over 2. So we get 36 integral, and I forgot my pi over 4 again, 0 to pi over 4 of 1 plus cosine 4 theta over 2 d theta. That was not a tough one to evaluate. If I'm just integrating, I end up with a theta and a sine 4 theta over 4. When I evaluate this out, I get 18 theta plus 1/4 sine 4 theta from 0 to pi over 4, and I get 9 pi over 2. So, double integrals in polar coordinates. We want to transform our region to polar coordinates. We need to transform our limits of integration to polar coordinates. And this quantity, RD theta, is our dA in polar coordinates. That's always going to show up inside your integrals when you transform your double integrals into polar coordinates. All right. There you go.